So good morning everyone. We'll continue from where we left off in the last lecture. We said the learning outcome for this week is actually identifying the fundamental principles of photon optics and quantify photon properties. But before we understand photon properties, we need to understand electromagnetic properties of light. So that's what we started doing yesterday. We said okay, light actually travels as electromagnetic waves, so it has to satisfy Maxwell's equations, and then we saw how Maxwell's equations would be satisfied for a particular structure. We took the example of an optical fiber, right. So we said if you consider an optical fiber, you can say that the light is essentially from a ray picture, you can say that light is confined within a waveguide through total internal reflection. But then we saw that you really have to consider them as waves, and so you need it basically accumulates phase as it's propagating, and to satisfy Maxwell's equations, you need to satisfy the boundary conditions, and as far as the boundary conditions are concerned, we were saying that you will have to have a consistent pattern of interference that is traveling all along the waveguide. So yesterday I wanted to actually show you this. This is something that I experienced as a student, and it stuck to my mind. But let's say this is one plane wave. We are trying to explain how this interference happens and how all these different modes develop. So let's say this is one plane wave traveling from this direction, from here to here, and now we have a reflection from another plane wave, right? And the reflection is such that they have a very small angle between them, right. So I'll move one with respect to the other. You see, let's say that the bright regions are where constructive interference happening, and the dark regions are where the destructive interference is happening. You can see that there is one pattern that's consistently developing across this. So this you may think of as your fundamental mode, right, and as you have steeper bounces, right, you are having one wave come across the other wave at an angle, and then you can start seeing multiple constructive and destructive interference fringes that are developing. And the key thought is that what we are talking about when you're talking about satisfying the boundary conditions is that this pattern, if it has to satisfy Maxwell's equations, it has to propagate all along the length of the fiber. Okay, so as you go higher and steeper angles, you have higher and higher order modes that are forming. But if you go back to a wave that's almost along the axis of the waveguide, then you have only one basically mode propagating, and that corresponds to a bright fringe at the center, and it goes towards the darker fringe at the edges of the waveguide. Okay, so this is sort of a very graphical way of seeing this interference, and of course you might have understood this through this picture itself, right. So we were talking about different modes, and of course this is a very simplistic picture just to show the how different modes essentially take different angles if you just go back to the ray picture, which is probably easier for some of you to understand, it takes different angles, and so we just came up with what should be that angle for a given mode, right? And but if we had to look at the true picture, analyze this a cylindrical dielectric waveguide that an optical fiber represents, if you were to do this more rigorously by solving the wave equation for cylindrical coordinates and looking at all the solutions, what you are essentially trying to get is this propagation constant as a function of this normalized frequency. Okay. So, we want to see which at any given wavelength which are the modes that are propagating, right. And we cut out a lot of details in getting to this point, but nevertheless just to understand what are the properties of these modes in this waveguide. So, if you look at this picture, we are saying that the fundamental mode would correspond to a Gaussian pattern, so which will essentially have a maximum intensity at the center, and it will trail off as it goes towards the edges, as it goes away from the center. And then we said, okay, beyond a V number of 2.405, you have the next mode, and so on, right. So, and the higher order modes and so on, right. So, yes, very good point. The question is about polarization. How does this work out here? So, I did not mention actually what LP means here. In this case, LP means linearly polarized modes. So, it so happens that the final modes that come out, this LP mode, in reality it is not a single mode. There are two different configurations consisting, what is technically it is called the HE11 mode. So, there is HE11 odd and HE11 even mode together constitute this LP mode. And when we look at the field configurations of this total mode, LP mode, the electric field is actually polarized in a linear manner. Okay. So, that is why these are called linearly polarized modes, but again, to understand the actual structure, we need to solve through the entire from the wave equations, which we are not doing as far as this course is concerned. Okay. So, one thing that I would also mention is, if we are considering a very thin waveguide, thin as in d, the diameter of the waveguide, which we have actually defined as 2 times a. If d is far less than the wavelength, right, then you would have a case where probably something like this is happening. We have a fairly large evanescent field, right, and maybe I should just write this here. So, this is probably what will happen when d is far less than lambda. What does that correspond to in terms of V number? V number will be a very low value. So, we are somewhere over here, right. So, effectively you have very little energy propagating the core, there is a large evanescent region, and when d approaches lambda, that is the situation we have where it's fairly nicely confined. And then there is this situation where d is far greater than lambda, and in this case you not only have the fundamental mode, you have the higher order mode and then the next higher order mode and so on. So, you have all these modes being confined within this this waveguide. Okay. So, that is what is happening for d much greater than lambda. So, just to illustrate that, but the key point that I wanted to make, maybe I said that towards the end of last class, but I did not emphasize enough, is a given fiber cannot be classified as single mode or multi-mode. Okay. It actually depends on lambda, and specifically this lambda over d factor. So, what is the dimension of the waveguide with respect to the wavelength? Okay. So, let us just take an example to illustrate that. Let's consider an example where you are given an optical fiber whose cutoff wavelength is given as 1200 nanometer. Okay. This happens to be the design of a standard single mode fiber that you use for telecommunications. All your optical communications is happening on a single mode fiber which will have a cutoff wavelength around 1200 nanometers, and let us say the numerical aperture is also given as 0.12. Okay. So, can you find the diameter of your waveguide if you are given this information? How do you proceed with that? So, at the cutoff wavelength, what is the V number? V equals to 2.405, which is actually given by 2 pi a over lambda multiplied by root of n1 square minus n2 square, which you can write as the numerical aperture of the fiber. Okay. So, if you substitute lambda equal to basically 1.2 micrometers is the wavelength, then if you substitute all the values given, you can find out that 2a would roughly correspond to about 8 microns. Okay. So, let us say we have this waveguide. In fact, this is one of the waveguides that we will be using in the demo and the lab experiment this week. So, this is a standard telecom fiber. So, let us see first of all what would be the, if you have a telecommunication wavelength, okay, telecommunication happens at 1.5 microns and beyond normally. So, if you want to look at what is the V number at 1.5 microns, you can simply write it as this is the V number at 1.2 microns, right, that is what is given, right, and so multiplied by 1.5 into 10 power minus 6 is the wavelength that we are interested in, and the V number at 1.2 microns is what we are considering. So, we put the corresponding wavelength over here. So, sorry, made a mistake here, it is the other way around. So, this should be 1.2 and this should be 1.5, right. So that is basically 2.405 multiplied by you can just say this is a factor 4 by 5 which would give you about 1.92. Okay. So you have a V number of 1.92 at 1.5 micron wavelength. Okay. So where are we now? So 1.92 is somewhere over here, right. So it clearly behaves as a single mode fiber, as you go to longer wavelengths. Similarly, if you want to look at the V number at 600 nanometers, what would that be if you use 600 nanometers? Right. So V number of so V number would have increased. Specifically, what is the factor by which it increases? 600 nanometers is a factor of 2 lower, so V number would have doubled, right. So we could have said, okay, V number would correspond to 4.8, right, and that would constitute a multimode waveguide. But in our experiments, we use a source which is 650 nanometers. So if you look at the V number at 650 nanometers, that's once again 2.405 multiplied by 1.2 in 10 power minus 6 divided by 0.65 into 10 power minus 6, and that would work out to be a value somewhere around 4.4. So in this case, at 1.5, it clearly works like the same fiber, right. It works as single mode fiber, whereas in this case it works as a slightly multimode fiber. And I should recall a funny episode related to this. So we have this kit here, this experimental kit, where the vendor essentially is setting up a similar experiment, and he sells some fiber as single mode fiber. He uses red wavelength. So he sells something as single mode fiber, and he sells something as multimode fiber, and then he sells something a special fiber, he calls that, which is slightly multimode. And over a period of time, we ended up damaging that fiber, so we were going for replacement, and he was actually charging us a lot of money for that replacement. And then we looked at this saying, okay, this slightly multimode fiber is what we normally use as telecom fiber, and we have lots and lots of telecom fiber in our laboratory. So why don't we just use that over here, right? And that's what you are doing. If you're doing that experiment today, you're using one of those normal telecom fibers. So there's no magic about designing a particular fiber for a particular application and all that. It may be something that was designed for some other application. If your wavelength is appropriate, you may still be able to use it. Okay, so don't buy into things which say, oh, this is generally single mode fiber, multimode fiber. If they are saying single mode fiber, watch where the cutoff wavelength is and where you are with respect to the cutoff wavelength, and then you can decide whether it's single mode for you or not.
So cutoff wavelength, if you decide, is the minimum value or maximum?
So the question is what does the cutoff wavelength imply? The cutoff wavelength implies that this particular point, right? So this is where lambda c is, right? So the lambda corresponding, which gives you for a given fiber, lambda gives you 2.405. So if you go higher V number, you have the possibility of the next mode also showing up, which is what we are calling a slightly multimode fiber. But if you have lower V number, which is corresponding to longer wavelength than the cutoff wavelength, then you can be sure you are working in the single mode regime. Okay. So that is one part. The other part is how do we couple light into an optical fiber? Okay, so let's just quickly look at that before we jump on to looking at photons. And maybe I can go to a new page for this. So coupling light into optical fiber. So what we normally do is, let's say we are basically coupling a laser light into an optical fiber. So you have a laser, let's say it is emitting close to plane waves. So what comes out of that is these plane waves, and it comes out with a particular radius. In the laser that we have has got a radius of a few millimeter, but then it has to couple into an optical fiber. Let's say we are coupling into a single mode optical fiber. Okay, what is the size of a single mode optical fiber for the wavelengths that we are considering? It's in the order of few microns, right? So a few millimeters need to be fitted into a waveguide which is few microns. You cannot just stick the fiber directly in the path of the beam, because it may couple something, but that would be a very, very small fraction of the light that's generated by the laser. So what do you have to do? If you want to fit this into the waveguide, use a lens, right? So you basically put a lens over here, a sort of a which brings the light into a focus. And what does the lens do? So this is a plane wave front. Okay, it goes through a material that is thick at the center and thin at the edges. So what does that do? The face fronts will be curved, right? So you would have basically the face fronts that are curved like this. Why? Because the central part of the wave is going through a thicker material, so it's going to be phase delayed with respect to what's happening at the outer edges, right? And that makes the beam come to a focus, and then it should diverge out. Now the question is, if you doing this in ray optics, you will basically put a ray that's coming down this way, a ray coming up this way, and it will show as if that ray is going to focus to a tiny spot. I mean, it's going to come to a point, an infinitesimally small point. But can you focus light to that smaller spot? What do you think? Have you tried focusing light? Yeah. So some of you have done this yesterday, right? And what you find is it doesn't allow you to go to a particular spot. There is actually a certain minimum diameter let us call this 2 W naught, right. There is a minimum diameter that you can get to. And why we get to a minimum diameter, explaining that, you have to go back to looking at this, right. So what does this signify? We are basically looking at the diffraction of light, right. So you can say that the minimum waist diameter that you are going to get is going to be limited by the diffraction of light. Okay, so there is going to be something called the diffraction limit that you are going to get into. Now, how do we quantify that diffraction limit, and then based on that, how do we figure out how to couple light into an optical fiber? Okay, so let's look at this. And before we do that, there is something else we want to do, is continue with this phase front. So this is actually going to, if it's converging like that, it's going to diverge in a similar manner on the other side. And what do you think is happening at the center? Clearly the curvature is changing sign, right. So you can say that at the center it's going to be close to a plane wave, or it is going to be a plane wave at the exact center, all the wave fronts. Okay, so that's interesting, because when it comes to a single mode fiber, right, and we saw how the single mode pattern would look like. What can you say about the wave vector for the single mode fiber? How many wave vectors are a single mode fiber represent the light that's propagating? Well, it's single mode, so it has to be one wave vector, and that's going straight down the center of the waveguide. So what does that constitute in terms of the wave fronts? It's a plane wave front, right? So what you have in a single mode waveguide is actually a plane wave front that's moving all the way across. So that's an interesting thought, because when you look at any of these optics, right, when you are trying to focus light to a spot, it gets to a plane wave front only at that spot, and then beyond that it starts showing this curve behavior. If you want to capture that plane wave front and transmit over a long distance, right, this optical fiber is a very nice way of doing that. It basically you capture it, you put that optical fiber right at the focal point, in which case you can be sure that you have a plane wavefront, and that's an essential condition, because if you come in with any other curved wavefront, only the plane wave component that's oriented along the center, only that component will couple down the fiber. All the other components will just radiate off, okay, because that's not, the waveguide says no, you're not allowed here, right. So only that component is thing, and so only when you put it at the focus, you have a plane wavefront, and that wavefront is caught, and that's consistent with the mode allowed by the waveguide, that's consistent with the Maxwell's equations for that particular waveguide, and then that is actually propagated all the way through. Okay. So before we get to some of the specifics, let's just examine what does this laser light represent. Now we said all waves, you solve what is called the Helmholtz equation and get a solution for the Helmholtz equation. One of those solutions corresponds to a Gaussian beam, okay. So, whenever we talk about these plane waves, we are talking only about the wave front. What is a wave front? Once again, the collection of points which have the same phase. Okay, if it represents a plane, then we call as a plane wave front, right? So there we are only representing the phase of the light. So far we have not talked about the amplitude distribution in the transverse direction, right? So if I am talking about a Gaussian beam, what does that represent? What do you think the amplitude or the intensity distribution is like? That's a Gaussian shape, so you know that the center is going to have maximum intensity and it's going to fall off. And it's interesting that the light modes that you get, the light beams that you get from a good laser which is operating at what is called a fundamental mode. This Gaussian mode is actually, we will see later on, is actually a fundamental mode for this waveguide itself, for the laser itself. And that mode is consistent with the mode, the fundamental mode for this waveguide. Okay, the waveguide actually, if you, I was mentioning yesterday, if you do the solving of the Maxwell's equations rigorously, you will find that the field shape corresponds to a Bessel function in the core region and a modified Bessel function in the cladding region. So together it will look like a Gaussian beam. So it would be nice to have a Gaussian beam source to couple into an optical fiber, because not only as the phase fronts have to be consistent, but the shape of your field pattern or the intensity pattern, that also has to be consistent with the waveguide. Okay. So you cannot take, let's say, a laser with a very poor wave front. Let's say you are taking a LED light, right? It's got very poor spatial coherence. The wave front is like all wobbly and all that. You cannot take that and expect to couple a lot of light into a single mode fiber, okay? Because that light source essentially has a non-planar wave front, okay? It's got multiple angles, and only one of those angles is consistent with what is supported in the single mode fiber. So you cannot do that. Whereas if you have a laser which is emitting its fundamental mode, okay, which happens to be in the Gaussian beam is a solution of fundamental solution of the laser cavity, then you can couple a lot of light into this optical fiber. Okay. So we can define a few things over here. So we can basically say, okay, let's define this optical axis, and if we look at this at the focal point, if we look at what is the intensity pattern that you get, we clearly said that has got to be Gaussian in shape. So it goes to a maximum and then it comes to a minimum. So let's say this is I over I naught, where I is, maybe I'll just write it somewhere else, where I is given by I naught exponential of minus 2, this is actually a function of the radial parameter, 2r square over w naught square. Okay. So that will be the intensity pattern. So clearly this would have a value of 1 at the center, and what would W naught correspond to in this picture here? 1 over E square value. So where I over I naught goes to 1 over E square, the corresponding radius would be called as the mode field radius, and the corresponding diameter would be called as the mode field diameter, right. So this would be this diameter here would correspond to the mode field diameter. Okay. So at this I said mode field diameter, but okay, let's just take it as the Gaussian diameter, because when I am defining an optical fiber, I am defining an optical fiber such that the core region is like this, the cladding would be somewhere like this, right. So I want to put the fiber core over here at the focus region, and I am saying that the mode that's supported by this fiber is Gaussian in shape, and that diameter, the mode field diameter within this fiber, that has to be consistent with the diameter of my Gaussian beam, the focused Gaussian beam, so that I can have maximum. So this also is like a Gaussian shape, right, and this will also have a mode field diameter. So if this diameter and this diameter are matching, that is when I have maximum coupling into the optical fiber. Okay, do you understand that? So the optical fiber will have a certain mode shape for its fundamental mode, and that mode shape is roughly a Gaussian shape, and so that Gaussian is going to have a diameter, a characteristic diameter, which we call as the mode field diameter, and that mode field diameter and the mode field diameter of my incoming beam, or the spot size at the focus of the incoming beam, has to be consistent for maximum coupling. So it is basically the overlap of these two fields that determines what is the coupling efficiency that I achieve. If I have a larger diameter, then clearly, if the focus diameter is larger, then clearly, you can see that part of the light is not going to be coupled into the fiber. But there is a misconception in general about this. People say if the diameter is smaller than this, than the size of the fiber, the mode field diameter of the fiber, then I should have high coupling as well, right? No, it does not work out that way, because what matters is the overlap integral of this field and that field. Okay, as long as that overlap integral is not matched, you do not have good coupling efficiency. But intuitively you think, yeah, I will just make sure that the spot size is lesser than the size of the mode field diameter of the fiber, and then I should have maximum coupling. Okay, so it does not work out that way. The other part that is typically important is the range over which the focused beam maintains a near planar wavefront. Okay, I say near planar because it can be a plane wavefront only at the center, but it's close to a planar wavefront around the center. So that is actually defined by a parameter which is called the Rayleigh range. So what is the Rayleigh range? So it is such that across this, so it's going from plus z naught to minus z naught, okay, it maintains a near planar wavefront, and it's defined, the Rayleigh range is defined such that at, so this is at z equal to 0, z I'm saying this direction is z, right, at z equal to 0 it's like that, at z equal to z naught the overall intensity pattern is like this. It takes a value, this is 1 when we are defining I over I naught, this is 1 and this is half. Okay. The overall intensity actually comes down by a factor of 2. That is what is known as z naught, and this 2 times z naught is what we are calling as the Rayleigh range. If we go back to now defining W naught, so this is the spot radius, right. If we look at the spot radius, now that has a dependence on what? Clearly that has a dependence on the angle, the angle at which I am trying to come to a focus, because if I have a shorter focal length lens, you can imagine that it is going to get focused to a tighter spot size, okay, as opposed to a lens that is that has a fairly long focal length. So you can basically write this as the spot size. If we go through that analysis, you can write the spot size, spot radius as given by lambda over pi times theta naught, where theta naught in this picture, theta naught would correspond to, if we say the size of the beam is d and the focal length of this lens, if we call that f, we can say that theta naught, especially if d is much larger than f, you can write this as basically d over 2 divided by f. Okay, so it's basically tan theta naught is d over 2 divided by f, but if d is far greater than f, so then you can write this as, so you can substitute that over here, and what you get is W naught is going to be given by lambda times f over pi times d multiplied by a factor of 2, and if you are talking about the spot diameter, which we are typically interested in, or the diameter which we want to match to the mode field diameter of the fiber, that is going to be given by 2 times W naught, which is 4 times lambda f over pi times d. Okay. So what does that tell you? Now of course you can get a smaller spot diameter if you go to shorter wavelength, which is Very, very important concept when it comes to what? Something to do with semiconductors. If you are making semiconductor chips, right, you want to define features in your semiconductor chip, and you go through a process called lithography, right. So, if you want to get better and better resolution in your lithography, you want to go shorter and shorter wavelength. So, you would see in the semiconductor industry, was using blue light, then ultraviolet radiation. Now they are talking about X-rays, using X-rays for your lithography so that you can get finer and finer features, right. And that's related to this. You can get a much smaller spot size as you go to much smaller lambda, but you also want to, you get a smaller spot size with smaller focal length and a larger beam to start with. Okay, D corresponds to the diameter of the beam. We can catch up in the next lecture. Okay, thank you.